Okay, so last time we were talking about the displacement current. So let me just recap briefly some of the things we talked about. So we knew Ampere's law, which related the circulation of the B field, right? Its integral along a closed loop to the current enclosed. And what we said was that Maxwell realized that in order to be consistent with the other equations as well as consistent with physical reality, there in fact needed to be an additional term, which he called the displacement current, which I'll denote by I sub d or I sub displacement. So just like you had a mu naught I enclosed, you had a mu naught I displacement enclosed. And in fact, that displacement current was related to electric field, specifically the rate of change of electric flux times epsilon naught. And what we saw as far as the direction went was that if your electric field was increasing with time, then the displacement current had the same direction as the E field. And so once you knew the direction of the displacement current, you could use all the usual right-hand rules. You could point your thumb in the direction of the current, and your fingers would curl in the direction of the B field. And if your E field was decreasing with time, then the displacement current would point in the opposite direction to the electric field. So any questions so far?
Does that mean that Ampere's law is incorrect?
Basically, yeah, that you can only use it in a case where you don't, like if you want to use the original Ampere's law, you can only do that in a case where you have no changing electric fields.
So why do we still learn Ampere's law if it's not correct?
Well, let me put it a couple of ways. One is the same reason why we still learn Newtonian mechanics, even though we know that later on it's superseded by special relativity and so on, quantum mechanics, is because for most of our purposes, it's actually still valid, right? It's not really that Ampere's law is wrong. It's simply that it's only we've learned the limits in which it is valid.
Okay.
Yeah.
Right, and the limit is that it only works when you don't have a change in the electric field.
Exactly. So as long as you have just steady currents and no changing charge distribution and all that, then yeah, you can use Ampere's law. Right, and one of the few cases we've sort of seen where we would need to apply the Maxwell correction is where you're changing electric field, is where you have a charging capacitor and you were looking at the B field near a charging capacitor. You would need to be careful and account for the changing electric field there. But as long as you just have a steady current distribution, then you can use the original Ampere's law because there's no changing electric field. Other questions?
Could you move the camera down so we can see the bottom of the notes?
Oh yeah, sure.
Thanks.
Mm-hmm. All right. So let's try a quick question. So share my screen. All right, so we talked about direction of displacement current. All right, so yes, so let's try this question. So I'm giving you an electric field and telling you how it's changing with time. And I'm asking at point P, which way will the induced magnetic field very divided. Yeah, let's go to the breakout rooms. I know this is a slightly confusing question. Remember though, the principle here that we're going to be using is this Ampere-Maxwell law. So it's this idea of displacement current, right? It's not a changing B field, it's a changing E field. So don't try and use Faraday's law, right? So I'll send you to the breakout rooms and discuss it. I'm gonna give you like a couple of minutes, discuss it, and then we'll come back.
Then on the left of P, and vertically they cancel out, then there's the ones on the right are going to go up, and there's more of them, so it goes up. That's what I said.
But then my question is, there's so the displacement current points out of the page, aligned with the electric field. But then wouldn't the induced current point in the opposite direction? Because the E field is increasing.
If it's increasing,
I think increasing goes in same direction.
same direction.
No, but I'm saying this is the displacement current. So wouldn't an induced current be the opposite?
Well, what induced current?
From the changing B field. I mean, changing E field.
So the changing E field tells you the direction of the displacement current. And then you can use, once you know the direction of that imaginary, that like effective current, the displacement current, you can use the right-hand rule to figure out the direction of the B field that it produces.
So you can consider the displacement current as an induced current from the E field.
We don't usually call it an induced current, but yeah, you can treat it as a current, and it produces a B field just like a normal current would.
Okay.
So yeah, it's a little different from Faraday's law, right? Where Faraday's law, you have a changing B field, a changing external B field that produces an E field that drives a current that produces its own B field, right? Whereas here you don't have all of that.
So yeah, I think C makes sense.
All right, cool. All right, we'll give everyone maybe another 30 seconds, and then I'll close the breakout rooms.
And did you have the same reasoning?
Yeah.
Cool.
All right. It's still very mixed. Pretty much every option got one. Okay, so let's discuss this. So what we have is an E field that is pointing out of the page, and we're told that it is increasing with time. All right, so this is a given external E field that is pointing out of the screen and increasing with time. So according to the rules for the displacement current, which way is the displacement current pointing?
Also in the positive k-hat direction.
Exactly, also out of the screen. All right. So if we point our thumb in the direction of that current, of that displacement current, so we point it out to the screen, we see that our fingers of our right hand will curl counterclockwise. All right. So we could expect that our B field lines are going to circulate, it's terrible drawing, but basically circulate counterclockwise. They won't be perfect circles. I know I've drawn them as sort of circular, but the idea is that they will circulate counterclockwise. And so we see that at point P, which is to the right of the center, we can see that the tangent of these curves will be pointing pretty much straight up.
How do we know that it goes from the center?
How do we know that it goes from the
Like, how do we know that the B field, like you were drawing the circles at the center?
Okay, all right. No, that's fair.
Because like I was picturing the B field somewhere else. So
I see. Okay. All right. I can try and clarify that the next time I guess I do that question, say that there's a region which is centered at some other point C, and then in that region, the electric field as a whole is increasing with time. Okay. That's a fair point. Yeah, if you don't know where the center is, if you don't know the extent of the region or where the center is, it's hard to tell. So I guess the idea was that it was just in this sort of boxed region. And so since you have, if we draw like a Amperian loop over here, we see that, oh, okay, there's some current enclosed, or displacement current enclosed, and that will generally cause the B field to go around in the counterclockwise direction. Other questions? Let me clear those drawings. So like I said, they shouldn't actually be perfect circles. They should be sort of slightly more squarish, maybe rounded squares. But the sense of circulation is the same. Okay. All right. So, cool. We have this correction term by Maxwell. Why then do we end up with all four? So let's actually summarize everything that we've learned. All right. So we have these are the four laws that we've learned. All right. We've learned quite a lot. Right? I mean, take a moment to take stock of what you've done in this semester. You've really learned a lot. This is like, decades of physics history. And we've learned Gauss's law, which relates the electric field through a closed surface to the charge enclosed. We've learned Faraday's law that relates the circulation of the E field to the changing magnetic flux. We've learned Ampere-Maxwell law, which we've seen some of the consequences now. We've seen, no one really has a name for this law. We often just call it the magnetic Gauss's law. Yeah, no one really has a name for it. This is the one that tells us that there are no magnetic dipoles. No magnetic monopoles, that are only magnetic dipoles. Yeah, so that you can't get an isolated North Pole or an isolated South Pole. So these are collectively called Maxwell's equations. So why did he get the credit? If he only really came up with this correction term, why did they suddenly label all four of them with his name? Part of the reason is, the main reason is that he realized that they collectively described the electromagnetic field, that electricity and magnetism were really two parts of the same thing, and that they had an astounding consequence. So the next few slides I'm going to show, I'm showing it to you partly so that you can get the conceptual idea, partly so that you have an idea of some of the history. It relies on some ideas from multivariable calculus. So if you haven't taken multivariable calculus, it's okay. We're not going to test you on that. But I do want to give you some of that history and some of that conceptual ideas of what Maxwell was able to accomplish. And in fact, when he accomplished this, he didn't have this neat vector notation. Okay. Surprisingly, notation in physics is also something that's evolving, right? So he didn't have this neat vector notation. He actually wrote all these equations out component by component. So he would write like ex dot dx plus ey dot dy plus ez dot dz. He'd write out everything. He wouldn't have this neat condensed notation. So he had much more than 4 equations. Yeah, so, okay, so what can he do? What could he prove with this? So if you learn a little bit of multivariable calculus, what you see is that you'll notice that all these equations have integrals over here, but you can use identities like the divergence theorem or Stokes' law and so on to actually rewrite these in a differential form. So this symbol here is actually a derivative operator. So here it tells us that the divergence of E is related to the charge density at that point. This is called the curl of E, is related to how the B field is changing with time at that point. And the curl of B is related to both the current density and the changing E field. And in this case, the divergence of B is 0, which again tells us that there are no magnetic charges. You only have B field lines going in closed loops. So these are the differential forms of Maxwell's equations. And once he had all of these, he noticed that you have, from Faraday's law, that a changing B field produces an E field. And from his correction term, we found that a changing E field would produce a B field. And so he realized that you could get a self-sustaining field there. So supposing you arrange, if you take a charge and shake it back and forth, then you will have an E field that is changing with time. And that will produce a B field. But if you're shaking it sinusoidally, then your resulting B field is also going to be changing with time. And so then that, by Faraday's law, will give rise to an E field. And because you can just keep taking derivatives of sine and cosine and just keep getting one after the other, right? That tells you that you can, it basically just keeps going back and forth. And so you end up with a self-sustaining electromagnetic field. You don't need charges or currents to keep your electric or magnetic field going. So if we look at Maxwell's equations and then we go to the vacuum, in the vacuum, there's no charge, so we're going to lose this rho epsilon term, where there's no current density, so we're going to lose this current density term. And so we end up with these four equations in the vacuum. And you can start to see that they're starting to look a little more symmetric, right? They're like, oh, this equation looks like this one starts to look a little bit like this one. And then what he did was he started plugging them one into the other. So he started out with this term, which is from the Ampere-Maxwell law. And then he took the curl of both sides. All right, so here you have curl of B, here you have curl of E, and then the time derivative. And using Faraday's law, he could relate the curl of E to the B field. So let me see if I can. Sorry. Okay, while I'm setting that up, let me just continue. So he related the curl of E to the B field using Faraday's law. So now both sides of our equation are in terms of the magnetic field. And on the left-hand side, we can use an identity from vector calculus to rewrite this in terms of the divergence of B and then this operator, which is called the Laplacian. And the divergence of B, we know, is 0. So we're down to just these two terms. And what's interesting here is that here what we have is a second order time derivative of the B field. And what we have here is a second order spatial derivative of the B field. Where did, there we go. Oops, sorry. Let me Control Z that and annotate. Just as a reminder, in our differential form, our curl of E is equal to minus partial B partial T. So that's what he was plugging in. So once he got curl of E on here, he just used this equation and plugged it in instead of curl of E. So you had one time derivative acting on another time derivative, which is how you end up with the second time derivative, and we picked up a minus sign over there. All right, so we have all of that. Now let me just clear that. Okay, and so this operator, it turns out once we get rid of the minus signs and all that, this is second derivative with respect to x plus second derivative with respect to y plus second derivative with respect to z of the magnetic field is equal to, and then we have the second derivative of b with respect to t over here. But this is the form of the wave equation. All right, now you'll see this in some more detail in waves and oscillations if you go on to take that course. But basically, this is the equation that describes a wave propagating. And what we see is that this constant factor out here should correspond to this factor over here, which depends on the speed of the wave. And so when he calculated the speed of these electromagnetic waves, he found that it depended only on, sorry, this constant factor out here only corresponds to this factor out here, which depends on the speed. And what he found was that he could calculate the speed from the values of mu naught and epsilon naught. And when he plugged those in, what he found for the speed was, in fact, a well-known speed, which was the speed of light. And so he realized that electromagnetism, well, first of all, electricity and magnetism were just two parts of the same thing, and that, in fact, electromagnetic waves were light waves. This was a huge revelation, and it united three big fields of studies. It united electricity, united magnetism, and united optics. This was one of the first great unifications in physics. So that's why he gets the honor of having all four equations collectively known as Maxwell's laws. All right, so like I said, don't worry about if you haven't taken multivariable calc, don't worry about the details there. Conceptually, what I want you to think about is that these equations are now, you have basically coupled differential equations. You have E depending on B and B depending on E. And so you have this situation where you can have E giving rise to B, giving rise to E, giving rise to B, and so on. And so you can get a propagating electromagnetic wave.
It only works if you differentiate the equation. Like the original forms don't do that, right?
The original forms, you can look at these and also show that you end up with a sort of wave equation, but it's much harder. The textbook does it a little bit, but it's much cleaner if you look at the differential forms. Other questions? What has this allowed us to do? So once we realized that electricity and magnetism were related to optics, then we could start to explain a whole lot of the laws of optics. And also we could start engineering materials that did what we wanted them to do optically. And so people have used this to create what are so-called metamaterials, which are very much engineered materials that have special properties and which can, for example, focus microwaves in better ways, create microwave lenses. And if you hear, like in the popular science media, talk about like invisibility cloaks and so on, then that's actually based on ideas from Maxwell's laws. They basically have created materials that allow light waves to bend seamlessly around an object. Right now, it's hard to do in the optical wavelengths. It's easier to do for longer wavelengths like microwaves or radio waves. So yeah, we can engineer materials that have the properties that we want them to have. And of course, once we realized this, then we came up with the idea of, using radio waves to transmit information. Yeah, so Hertz, I believe, was the scientist who first showed that the electromagnetic waves were indeed a real thing. He showed that if you have a discharge of, like if you suddenly discharge a capacitor, right, that's a sudden change of electric and magnetic fields going on there. And he showed that that could create a spark on a separate circuit that was like physically not connected at all. but like discharging one circuit could create a spark on another because of this transmission of electromagnetic energy. And so that brings us to a crucial point that these waves are real things, right? Light is a real thing, it carries energy. And so that brings us to our next concept, which is the idea of the Poynting vector. So Poynting here, the reason it's spelled with a Y is it's named after a person, but it's a nice name because yes, it actually points in the direction in which energy is flowing. So it's typically denoted by S vector, and we see that it's given by E cross B times 1 over mu naught, and that gives us the direction of the Poynting vector. So right now this is sort of abstract, so let's look at an example. So let's say we have a current carrying wire, and we see that, okay, there is a region with electric field pointing like this, the yellow vectors, and we have the B field circulating around it due to the current. So first of all, does this section of the wire have a resistance? Just call it out, but be able to justify your answer.
I thought we said have resistance.
Say again?
Like, are we talking about like a good wire?
Well, the presence of the electric field should tell you something.
Oh, right. Okay. So this is an ideal wire.
Anyone? So if there's an electric field, what does that tell us about the potential?
There's a potential difference.
There's a potential difference, right? And so we have a potential difference going on over here. And so then that means there's likely a corresponding resistance involved. So yeah, so we have a potential difference, and where there's a potential difference, there's electric field. And so we have electric field and magnetic field. So let's look at the direction of the Poynting vector. So if I look over here at the top of the wire, I see that, okay, E is pointing along the wire in the direction of the current. B is pointing, at this point, it's pointing to tangent over here. So try using your right hand to figure out the direction of E cross B. So you have E cross B. Is it pointing into the wire or away from the wire?
Into the wire.
It is pointing into the wire. Let me show you in a slightly.
A question. Why do we care about the resistance?
Oh, well, just so that, I mean, we have a clear potential difference and thus a clear electric field.
Even though you told us, just so we understand why we have the electric.
Right, the presence of the electric field reminds us that, oh, there must be a potential difference here. And,
okay.
Yeah. So, why potential difference implies resistance? Well, because if you have a wire with a potential difference and a current flowing through that, then we know that those two things are related by Ohm's law, which tells us delta V equals IR. But yeah, it was more just a reminder that if you see an electric field, you know that there's a potential difference. Okay, so let me just draw that wire from a different perspective. So let me say I'm looking at the cross section of the wire. So then the current is coming out of the page. So we have Yeah, so current coming out of the page. So the electric field is coming out of the page, and that's E field. And we know that the B field is circulating counterclockwise. That's the B field. So now if I look at this point, I know that the B field is pointing to the left, E field is pointing out of the page. So if I do E cross B, it's not easy. If I do E cross B, no, hold on. Here we go. All right. E pointing out of the page, B pointing to the left. And so if I look at the way my thumb points, I see that at this point it's pointing down into the wire. If I look at the corresponding point at the bottom over here, now the B field is pointing this way. And again, if I look at direction of the E field and direction of the B field, I see that the pointing vector is now going to point, again, into the wire. So the pointing vector tells us the direction of flow of the electromagnetic energy. And so this is telling us that electromagnetic energy is flowing into the resistor, which in a way actually makes sense, because what does a resistor do? It takes some of that energy from the current and it converts it into heat. Right? So it's absorbing electromagnetic energy and converting it into heat, into just like the kinetic energy of the atoms in the resistor. Let's look at another example. Supposing we have a solenoid and it's not in a steady state, right? So the current is either increasing or decreasing, right? And so we know that, oh, if there's a changing B field, there's going to be an E field. So I've given you the direction of the B field, of the current, of the B field, and of the E field. And I'm asking, oh, is this current in the process of increasing or is it in the process of decreasing? So it's kind of split. So let's, well, okay, can anyone want to justify their answer?
I'll try.
Okay.
I was thinking if the B field's coming out, that means that the B field from the current has to be moving clockwise around the current.
Say again?
If the B field's coming out of the page, then
Yes.
the B field is going clockwise around the current.
Mm-hmm. Wait, the E field is going clockwise around the current.
Or the B field is going clockwise around the current. Sorry. The B field's always going clockwise around the direction of the current, and so for it to come out, the current has to be moving in the same direction as the E field. And so if they're in the same direction, then the current. Oh, wait, I'm sorry, I got it confused. Never mind.
Anyone else?
I have a question.
Yes.
Is this different? This isn't the I displacement current. This is just I, right?
This is just I. Yeah. This is an actual solenoid and a current running through that solenoid. And we know the direction of the current. We just don't know if it's increasing or decreasing.
Oh. Okay. I voted different. I don't know.
All right. So it is a little confusing. So let's look at this in two different ways. So remember, what's given here is that we have a current in the solenoid, which is creating a B field. And that because this current is changing, this B field is changing. So which of the four Maxwell laws is going to be relevant here?
The one with the displacement current.
Remember that the displacement current happens if you have a changing external E field.
An external E field.
Right. I mean, like the E field is given to you and we know that it's changing with time and that produces a B field, right? Here, what we have is we have a current that is producing a B field and that is changing with time. So that's what's given to us, right? And then that's producing an E field.
How do we know that the B field is changing?
Well, because we know that a steady B field would not give rise to an E field.
Okay.
All right. So if we think about, okay, which of Faraday's laws relates a changing B field to an E field, then we see, oh, okay, that's Faraday's law, right? Looking that in more traditional form. Yeah, we know that a changing magnetic flux will give rise to an electric field. All right, so let's think about what Faraday's law tells us. Faraday's law tells us that, remember, the easy way to remember the whole thing was like fight the change. So here, if we put a second loop of wire here, this E field would drive its own current in that loop of wire. And which direction would that be? That would be in the same direction as the current in the solenoid, right? And so it would be trying to create its own induced B field, which would be pointing out of the page as well. So it's helping the external field. When does that happen? That happens when you have a decreasing external field. Then that's when the loop tries to respond by keeping the magnetic flux the same. I know now that we have 4 Maxwell's laws, it's a little tricky. We have to think carefully about which one is appropriate. So
Wait, can you explain? So the E field, can you explain about how you figured out the other I from the E field again?
Sure. So the idea is that if I put an imaginary loop of wire here, then if it's a conducting loop, then the electric field would move the charges in that conducting loop. And so it would drive a current in the same direction.
Because of the right-hand rule?
No, more because of F equals QE, right? So if we put a positive test charge here, it's going to feel a force in the same direction as the E field. And so you
right,
end up with
okay.
a whole bunch of charges moving like this, but moving charges are a current.
Right, okay.
So you end up with a current circulating again counterclockwise, and that would produce a B field, which is out of the page.
Right, okay. And then based off of Lenz's law, you know.
Exactly. Yeah, we know that the induced B field will line up with the external B field if the external B field is decreasing.
Right.
All right. So I'm going to present this in a couple of different ways. So, okay, so that's one way of thinking about it. We could also think about it just in terms of inductors. We know that a solenoid is basically an inductor. So you can ask, okay, this E field, is it trying to help the current or is it trying to oppose the current? And we see that, oh, this E field is in the same direction as the current. It's trying to help it, right? But we know that in an inductor, it doesn't want the current running through it to change, right? So if the E field is trying to help the current, that must be because the current is decreasing. And so this E field is trying to keep the current going.
How do you know that the E field is trying to help the current?
Because it's in the same direction as the current. So
Right.
it's trying to push the charges, continuing to push them in the same direction.
Because F equals QE.
Because F equals QE, exactly.
Okay.
And if the E field had been pointing in the opposite direction, then we would know that this electric field was trying to slow the current down, was trying to decrease the current. And so that would be if your current was increasing and it didn't like, the inductor doesn't like the current to change, so it tries to stop that change. All right, so we've looked at it in terms of Faraday's law. We've looked at it in terms of inductors. But I said this whole section was about the Poynting vector. So how does that relate to this? So if we calculate the direction of the Poynting vector, so if I calculate it over here, remember it's E cross B, right? So if I calculate that, what I see is that let me choose a different color, green. Yes, okay. What I see is that the direction of the Poynting vector is like this over here. It's like this over here, like this over here, like this over here. So it's pointing away from the empty space into the wire. So that tells me that the energy is flowing from the magnetic field. Remember, we said that magnetic fields can store energy. The energy is going from the magnetic field inside the solenoid, going back into the wire. So in other words, the energy being stored is decreasing. So the current must be decreasing. All right. So looking at the direction of the pointing vector tells you about the direction that the energy is flowing. And so here it tells us that this, remember, the green arrow here represents the pointing vector. The energy is flowing away from the not empty space, the magnetic field inside the solenoid. It's flowing away from that into the wire, right? So it's going back into the circuit through the wire, but it's leaving the magnetic field. And so that tells us that the current is decreasing. All right, I know this was tricky. So questions?
Can you repeat? So when it's going from a B field to a current, that means the energy
is leaving the B field. So the B field is trying to supplement the current.
okay.
Right. So the current is weakening, and so the B field is trying to like give up its energy and supplement the current.
Okay, I see.
All right. So one last example. We have just a couple of minutes. So one last example. So this was here we have a solenoid with a changing current. You can imagine that the corresponding situation would be if you have a charging or discharging capacitor. And so here is a similar case. So let's very quickly just poll on that. All right. So most of you voted for increasing, which is correct. And so remember here what we have is a capacitor. So this general thing we'll have between the plates is an electric field. And we only get a magnetic field if that electric field is changing with time, right? And so that which of Maxwell's laws does that involve? Where you have a changing E field gives rise to a B field. Anyone? Come on.
Ampere's law.
Ampere's law, right? This is where Maxwell's correction to Ampere's law comes in. We have a changing E field will give rise to a B field. So here, this direction of this B field must be due to the displacement current. So we can use the right-hand rule. We see that, oh, well, this B field is circulating counterclockwise. So that tells me that the displacement current must be pointing out of the screen. And then I see that, oh, my displacement current is in the same direction as my E field. When does that happen? Displacement current is in the same direction as the E field if your E field is increasing with time. But we know that if the E field is increasing with time, what causes the E field? It's the charge on the capacitor plates. So the capacitor plates must have an increasing charge. And so the charge on the capacitor plates is increasing. Now, if we look at it in terms of the pointing vector, what we see is that at this direction, if I do E cross B, let's see, E cross B, yes, the pointing vector is pointing inward, is pointing inward, is pointing inward, is pointing inward. So we see that, oh, there's more energy coming into the space between the plates. And so there's more energy being stored in the electric fields between the plates. And so that must mean that the capacitor is being charged. And so the charge on the capacitor plates is increasing. So a slightly more rigorous way to do it is from Maxwell's laws, but the Poynting vector gives us a sort of quick way to see which way the energy is flowing. Okay, that is, we're past time, so we'll stop there. If you have questions, stick around to ask. But otherwise, we're done for today. Thank you all.
Thank you.
Hey, Liam.
Sorry, I was on mute.
Oh, that's fine.
Sorry. I actually have a question.
Yeah, sure.
Well, it's a quick question about both my schedule and some physics.
Okay.
So I was wondering, just like, if you could give me like a conceptual sentence on how an induced current works, like one that could describe like how and when an induced current is like brought up. Is
Okay.
it always because of a changing E field or a changing B field?
Sure. Okay. Okay, so I would say that, all right, if you have a changing B field, right, if you have a given external B field and it's changing with time, then Faraday's law tells us that this changing B field is going to give rise to an E field.
Yes.
Now, if there are conductors nearby, the E field will act on the charges in those conductors and start to move them and create an induced current.
Okay.
Right? And if you have that induced current, well, that current will produce its own induced B field and so on. But that's only if there are conductors nearby. Faraday's law, what it tells us is that as long as you have a changing B field, you're going to produce an E field. Now, whether that will give rise to something else depends upon whether you have conductors nearby.
Okay. Got it. All right. Thank you.
You're welcome.